Welcome to iLecture Online. Our next topic in the chapter of gravity is called the gravitational potential energy. Now, it is different from what we've seen before. Before, you might have seen the equation where potential energy is equal to mgh. And of course, that is correct as long as the gravitational acceleration doesn't change over the height difference. That is, of course, not the case when we're dealing about moving something from one orbit in space to another orbit in space. The change is so large that the acceleration of the gravity g is not a constant. And since it's not a constant, we can no longer use this equation for calculating potential energy like in space. So what we have to do instead is we have to actually calculate the work done to get an object. Let's say this object has mass m, move it from one orbit where the radius is r1 to another orbit where the radius is r2. So what is the work done to do that? And the work done is going to be equal to the integral of all the little dw's, all the little small amount of work done by moving this mass incrementally through small little changes, small little dr's. So the work done, of course, is equal to force times distance, but to do a small amount of work over an infinitesimally small amount of distance is f dot dr. And of course, these are vectors, and we have to integrate that from r1 to r2. So we're moving something from radius 1 to radius 2, or orbit 1 to orbit 2. Now, of course, f dot dr is f times dr times the cosine of the angle between them. So this is equal to the integral from r1 to r2 of the force required to lift it up times dr times the cosine of the angle between them. Now, since the force required to lift this mass up to a higher location is in the same direction as the motion, the angle between them is 0, and of course the cosine of 0 is 1, so we can simply go ahead and remove that to be 1. And the only other thing we have to do now is plug in an equation for the force, and of course the force there is the universal equation of gravity, which now means that the work done to move something from orbit 1 to orbit 2 is equal to the integral from r1 to r2 of the force, which is g small m big M over r squared times dr. Okay, now of course maybe I should use big R instead of small r so that the variables remain the same. It doesn't really matter. Let's call this big R here. Let's call this big R there. So that way, let's call this big R here. So that way we stay consistent. Okay, now g, m, and big M are all constant. They can come outside the integral. And r to the second power in the denominator can move to the numerator. So this can now be written as the work done is equal to g, m, big M, times the integral of r to the minus 2 dr, going from r1 to r2. And now we can go ahead and integrate that. So the integral of r to the minus 2 is equal to g, m, big M, times r to the minus 1 divided by the new exponent minus 1. And of course, evaluate from r1 to r2, and then rearranging that a little bit is equal to minus g m big M over r, evaluate from r1 to r2. And writing that in, plugging the upper limit, we get minus g m big M over r2 minus g m big M over r1 squared. Nope, not squared. Sorry about that. No square there at all. All right. Now, since one is positive and one is negative, because this minus times this minus makes that a positive, I can say that the work done is equal to, I'm going to write this one first, so it's equal to g m big M over r1 minus g m big M over r2. All right. So the work done looks like it's going to be equal to the potential energy at this location minus the potential energy at that location. That would be the work done. Now, in physics, to make things easy, what we're going to do here is have some sort of reference point. Remember, when we use this old equation right here, the reference height was the surface of the Earth or the surface of the table, wherever we started from. But in orbits, what we're going to do here, and this is standard notation, we're going to assume that the standard potential energy is equal to 0 when the distance is at infinity. So we're going to say that the potential energy is equal to 0 when r is equal to infinity. So what we're going to do now is set R2, because of this, we're going to set R2 equal to infinity. So we're going to put the position where we're going to lift this to out to infinity, from some place, R1, out to infinity. And of course, at that point, the potential energy is 0. So that means that this quantity right here, the potential energy of this quantity right here, is going to be equal to 0. So now we're going to say that the work done is equal to Gm big M over R1 minus 0. Because we're going to set R2 at infinity. So now R2 is at infinity. Now what we've done is we've discovered that the work done to take an object from here out to infinity takes this much energy. That's how much work it takes, that much energy to get it out there. So therefore, what is the potential energy at this location relative to a point at infinity? Well, if the potential energy at infinity is equal to 0, then anything below that must be a negative potential energy. So the closer you come to the Earth, the lower the potential energy is. Now, if it takes this much energy, Gmm over R1, to go from here to there, then to go from 0 to here, it must be minus that amount of energy. So therefore, we can say that at R1, the potential energy therefore must equal the negative of this quantity, which is Gm big M over R1. And so that is now our definition of what we call gravitational potential energy. The potential energy of any object at any point in space, relative to a planet or a star or anything else, is going to be equal to minus Gm big M over R1. So as an example, let's say we place an object right at the surface of the Earth. So therefore, in our example, R1 is going to be equal to the radius of the Earth. And let's say that the mass is equal to 1,000 kilograms. What would be the potential energy of that object on the surface of the Earth using that definition? Well, we plug in the numbers. So this is going to be equal to minus G, which is 6.67 times 10 to the minus 11, times the small mass, which is 1,000, times the big mass of the Earth, which is 5.98, times 10 to the 24th. Notice I left off the units because I'm running out of room. Divided by the radius of the Earth, which is 6378000. That's in meters. And of course, the units of that will then be joules, because we're talking about potential energy. Looking for my calculator. All right, so 6.67 e to the 11 minus times 1,000 times 5.98 e to the 24th divided by 6378000 equals, and that would have a potential energy of minus 6.25 times 10 to the minus, not minus, but plus 10 joules. So, let me try that again. So that'd be plus 10 joules. And that would be the potential energy of a 1,000 kilogram object on the surface of the Earth, which then means that if you want to take it from the surface of the Earth and move it away from the gravitational effect of the Earth, you would have to put in this much work to get it moved to that point. And that's the definition of gravitational potential energy.